Hey everyone, so my name is Annika and we're looking at chapter 7, which is circular motion and gravitation. So this chapter is going to have 4 main sections. We'll look at centripetal acceleration, and then we'll do Newton's law of universal gravitation, motion in space, and some torque. So we're going to start with centripetal acceleration. That's the first section of chapter 7. So we'll start by defining circular motion. That's any object that revolves around a single axis, which is known as an axis of rotation. So for example, over here we have a ball that's sort of spinning around this axis, and we'll call the axis in the middle the axis of rotation, and the ball is in circular motion. So when an object is moving in circular motion, the tangential speed is defined as the speed of the object along an imaginary line that is tangential to its circular path. So this is sort of similar to the velocity as we've defined it in previous chapters. And it's just in a circle, it's slightly different in that it's drawn sort of tangent to the circle. So that's how fast the object is moving at any given point. And you could think of this as like if a car is moving around a round track and it's going 60 miles per hour, that's its tangential speed. And we say that when an object has constant tangential speed, it doesn't change, it's in uniform circular motion. There are a few factors that influence tangential speed. So first of all, the object's distance from the center of its circular path influences how fast it has to move. So we can take this example of a track. I've drawn it as a perfect circle here, but in reality tracks are not perfect circles. And we have these two runners, and one is moving in lane 1, which is the closest lane to the center of the track, and the other is running in lane 8. In order for them to stay next to each other, the runner in lane 8 would have to move faster because he's traveling around a longer path. So at this point you might be wondering why an object in circular motion is accelerating even when its tangential speed is constant. So as we've learned from before, acceleration is defined as a change in velocity, and we also know that velocity has both magnitude and direction. So rather than being a change in magnitude like the acceleration we've looked at before, centripetal acceleration results from a change in direction of the object's motion. So let's take a look at how that works. Here we have some object that's moving around a circle, and I've drawn its velocity in red at multiple points around the circle. As you can see, it starts with a velocity pointing this way, and then as it moves around the circle, the velocity changes in direction, even though its magnitude is always the same. So that's how we know that the object is accelerating when it's moving in a circle. We define centripetal acceleration as acceleration directed towards the center of a circular path. So in other words, if we have this circle, as I've drawn here, the centripetal acceleration, or a sub c as we write it, will be pointing towards the center. And we have this equation over here for centripetal acceleration. It's a sub c, or centripetal acceleration, equals tangential velocity squared divided by radius. And this radius is just the radius of the circle, or the object's distance from the central axis. So the following equation proves why the acceleration of an object in a circle will always point towards the center. So we know that acceleration, or a, is a change in velocity. Delta v is the final velocity, which I'm calling v2 here, minus v1. So the way that works in a circle is we have these two velocities. One moment the object is moving in that direction, and the next it has v2, which is pointing in a slightly different direction. So if we're solving for acceleration, we would want to do some vector subtraction. So we would take v2, I'm drawing it a little bit bigger here, and then subtract v1, so meaning adding its opposite. So it's usually pointing in that direction, and now we're pointing it the other way. As you can see, when we subtract these two vectors, the resultant, using the head to tail method, is pointing straight down, or towards the center of this circle. That kind of shows how the direction of this acceleration works. Another type of acceleration for objects in circular motion is tangential acceleration. This is acceleration due to a change in speed, so magnitude of the velocity rather than the direction, of an object that's in circular motion. So we can take the same example of a runner on a track. If he's moving at v1 and he accelerates tangentially, his new velocity, v2, we'll call it, will point in the same direction but with a greater magnitude. So we know from Newton's second law that any object that's accelerating must have some net force acting on it. In a circle, we define this as centripetal force, which is the force that keeps an object moving in a circle. So the example we use most commonly in physics for this is a ball and a string. Say we have this person who's rotating a ball in a perfect circle on a string over their head. Something must be keeping the ball moving in this circular path. So I've drawn the ball and the string a little bit bigger over to the right here, so that you can visualize that the force of the person's hand over at the end of the string on the ball is the centripetal force that's pulling the ball towards the center of its circular path. In other words, keeping it moving in a circle. So I've broken down this equation using Newton's second law, force equals mass times acceleration. Here, the force and acceleration are centripetal. And then you can see I've plugged in the equation from before that we got for centripetal acceleration. So that's v tangential squared divided by r. Now, if we plug this in to the centripetal force equation, we get that centripetal force equals mv squared over r. That's going to be a very useful equation coming up. And just a note, centripetal force is the net force on objects in circular motion, and it will always point towards the center of the circle, or the axis around which the object is rotating. Now let's do some practice problems. Number 1. A rope attaches a tire to a tree limb. A girl swinging on the tire has a centripetal acceleration of 3 meters per second squared. If the length of the rope is 2.1 meters, what is the girl's tangential speed? So we're going to solve this using the equation for centripetal acceleration, which is tangential velocity squared divided by r. Now we know the centripetal acceleration, that's 3 meters per second squared. And we also know the length of the rope, which we'll call r, because that's sort of the radius between the girl's position down here and the center of this circular path. So that's 2.1 meters. Now all we're solving for is this v tangential squared. So we can multiply this 2.1 over to the other side to simplify this fraction. So we get 6.3 equals tangential velocity squared. Take the square root of both sides, and we find that the tangential velocity of the girl on the swing is equal to 2.5 meters per second. That's how fast she's moving. Number 2. A child rides a merry-go-round of radius 1.5 meters. If the child's tangential speed is 1.5 meters per second, what is his centripetal acceleration? So this time we know the radius and we know the tangential velocity, and we're solving for acceleration. So we'll use the same equation, which is centripetal acceleration equals tangential velocity squared divided by r. Now we can plug in our numbers. We have a tangential speed of 1.5 meters per second, so we square that, divided by 1.5. And then as you can see, if we're squaring 1.5 on the top and we have 1.5 to the first, this is all going to cancel out to equal 1.5. So the centripetal acceleration will come out to 1.5 meters per second squared. Number 3. A dog runs in a circle of radius 1.5 meters at a tangential speed of 1.8 meters per second. If the dog's mass is 18.5 kilograms, what is the magnitude of the centripetal force on the dog? This time, we'll use the equation for centripetal force. F centripetal equals mv squared over r. Now we can plug in the numbers we have. We're looking for centripetal force. We know that the mass is 18.5 kilograms, and then the velocity is 1.8 meters per second. We'll be squaring that. And then in the denominator, we have 1.5. If I plug in all these numbers to the calculator, I get that the centripetal force on the dog is approximately 40 newtons. That's what's keeping the dog moving in a circle. So this next problem is one that comes up in AS Physics at Menlo Atherton High School. It says, a woman of mass 70 kilograms rides the amusement park ride drawn below. Find the tangential velocity of the ride if frictional force allows the woman to remain attached to the wall as she spins. So basically this is one of those amusement park rides where people stand around the perimeter of a cylinder, and then as they spin around, they're kind of stuck to the wall by the force of the ride. So if we look at it a little bit more closely by drawing a free body diagram for the woman, we see that she has some weight, mg, that must be canceled out by an upward frictional force that's going to keep her from just sliding down the wall of the ride. And then we'll also have some kind of net centripetal force, because that's what's keeping her in motion in a circle. So let's start by setting these forces equal to each other in the vertical direction, because we know that the woman isn't moving in that direction. So we have mg equals frictional force, which is defined as mu, or the coefficient of friction, times normal force. And we know in this situation that normal force comes from this centripetal force that's coming out from the wall of the cylinder. So that's what we're going to use when we calculate friction. So now we can simplify this a little bit, and we'll get mg equals, if the normal force is centripetal force, that is mv squared over r. So we'll plug in mv squared over r, and then multiplied by mu, which is the coefficient of friction. So we can cancel out the m's because they appear on both sides, so the mass of the woman becomes irrelevant. And now we're left with g equals v squared over r times mu. So we'll approximate g to 10 for this. We're solving for the velocity of the ride. We know that its radius is 2.1 meters, and the coefficient of friction is 0.4. So now we're going to divide both sides by 0.4. We get that 25 equals v squared over 2.1. So finally, I'll multiply this 2.1 over to the other side and take the square root of both sides. And we get that the velocity of the ride is 7.25 meters per second. That's its tangential speed.